Okay, well, there's Carl here. He will talk about exploring the topology of Scottish Gaelic dance. I should say that until Julia had this vision, I had no idea there was a connection, but now it's obvious. It would be even more obvious after the talk. Thanks.
Well, we've now had two presentations about topology, first in the real world and as applied to visual objects, and now we can maybe also apply topology to movements. So I'm going to talk about how Cayley's can be analysed using braids. So you see a braid there, but first I'll explain the structure of my talk. So I'll give a brief introduction to the whole idea of how to do this and to the concepts that are used in the talk. Then I'll explain how I analysed the Cayley's with the braids. And at the end, I'll also talk about the applications of how this can be applied to computer science and to, in particular, to robot motion planning. So let's start with a definition or an explanation of what a braid is, mathematically speaking. So we have a certain number of strands running from top to bottom, usually. They are not allowed to intersect at any point, but there is a prescription of how they cross over each other. And this is described by symbols giving a so-called braid word. So the subscript denotes the strand that is crossing, and there's a positive power, which means that it's crossing over the I+1 strand, and a negative power, which means it's crossing under the I+1 strands. Also, the strands are not allowed to turn back up, so you can always, you only go downwards. As you can already guess from the notation, those are inverse operations. So if you have first going over a strand and then the other strand going under again, then they undo each other. So in particular, we can sort of move the strands around as long as we don't we don't move them out of the frame in which they are kept. So we have equivalent braids if they're related by a sequence of pushing and pulling, and the trivial braid, which is quite important, is that all the strands run parallel. And very interestingly, the braids of n strands form a group. And yeah, well, it's fairly obvious that if you combine two braids of n strands, you get another braid, so you have closure. They are associative, so that's fairly easy to check as well. I already mentioned the inverses, so you can just by reversing everything you did to the strands, you get back to the trivial braid, and the identity is just the trivial braid. So the idea is now to analyse the Scottish Cayley dances. I'm afraid I can't give a mathematical definition of what a Cayley dance is, but we look at what braids arise from Cayley dances. So there's this tradition in many alpine regions where people dance around a maple braiding strings. This should be a video if it works.
Yeah.
So you can see the dancers are moving around and braiding the strands as they go. And it gives very nice patterns as well. So the interesting part is that you can associate with the movements a certain way of braiding the strands, and you can sort of move forwards and backwards. So you can get from a braid to a dance and from a dance to a braid. So in the theoretical part of this project, I took a number of Cayleys and described them with this method, and then looked at the mathematical properties of the braids. And then the second part is actually why we do this. Braids have been used in motion planning and in collision avoidance algorithms because they give a way of moving around without colliding one another. I'll make that idea more precise. We're not talking about this kind of robots, but more these robots. And yeah, in the frame of this project, the insights that were gained from analyzing Cayley's through braids were implemented in, or yeah, were tried to be implemented in a simulation program.
Are these yours, Ram? Are these yours?
No, but
No, somebody
there are
else's.
some in informatics that we can. Yeah.
Okay, so in the theoretical part, I'll first explain how you can get from a Cayley to a braid, and then I'll talk about some problems that arise from that. I'll briefly mention the results of the mathematical analysis of the braids, and perhaps if time permits, we can talk about a trivial Cayley as well. So the method is, you start with a description of the dance. So there's an internet encyclopedia that has describes many Cayleys, and there's a particular way of describing Cayleys apparently with very complicated symbols. But once you get used to that, it's easy to understand. In the example I'm going to talk through now, we're going to focus on the reel of 3, which is the 4th frame. And I'll just explain how that would translate into a braid. So I apologize for poor draftsmanship in advance, and some of the animations got mixed up when transferring my computer to this one, but we'll fortunately have a real life illustration of that as well. So we first number the dancers and then associate. We choose a vanishing point, so this is where we fix the strands that the dancers hold. So then we draw the ribbons. And now the important thing happens, we need to map this to 2D, so we rearrange the dancers with the ribbons. And then basically we follow the dance as it unfolds. So perhaps if I could get 3 volunteers to illustrate the we need one
You
more
can be the
person.
vanishing point because you're really tall. Blue, are you looking blue today?
Thank you.
I mean, green or red? Okay, so you should hold one end of the ribbon. Each hold.
So we need to stand in a line.
Which way?
Yeah, you're the vanishing point, so this would probably, yeah, that's
Sure.
good. Okay, and then we pass right shoulders first.
Okay.
Yeah, so we dance the Cayley, or the reel of 3 rather, and we braid these strands. Yeah, and as you can see, we now have a braid. And in fact, this is just the usual braid that you find practically everywhere on jumpers, in hair, and whatever. So,
Bread.
was that clear? Or?
So
Bread.
do you want to describe in slow motion what we're doing with the reel of 3?
Right. So if we pass right shoulders, and we say you're the first strand, and I'm the third strand, then this corresponds to, if we're looking on the braid from your side, this motion corresponds to sigma 2.
So 2 and 3 swap places.
2 and 3 swap places, and the second strand passes in front of the third strand, giving you sigma 2, and then we pass the other way round. So this is now sigma 1 inverse, and then the whole thing repeats again. Yes. So the resulting braid word from this, from 2 swaps, is sigma 2, sigma 1 inverse, and then you can just repeat that. Thank you very much. There's also full animation of this. So here you can see the wheel of 3. As you see the movement now, there won't be any need for the video. So yeah, it depends on how you start in the wheel of 3, what braid work you get. If you start with the outermost person, or if you start with the inner person, just gives different braid work. So here's also an animation of what happens. You see that the dancers swap. This is the way in which they swap places, if you look at them from above. And then you can also trace what happens to the braid. And here I apologize for the poor drawings, because I mentioned earlier that strands are not allowed to turn back up again, but yeah, that's there. So there are a few problems associated with this method. There are a few decisions that have to be made. So the first thing is the mapping. How are you going to map this, these strands, which are 3-dimensional here, to 2-dimensional braid? Because it depends on where you place your focus. So as before, when we have the braid, if we look from your side, from the side of the audience, that's a different braid than if we look from this side. So that is one decision. Another important decision is how you number the dancers. So there's no way of making sure that the numberings don't influence the braid that you get. And lastly, there are also a lot of ambiguities in the dancers. So for example, instructions like polka around the room, you don't really know what happens. And this all is manifested in a problem that we don't do. So all of these decisions give different braids, and the braids are not mathematically equivalent. And I haven't found a way of ensuring that you can get from that one K-lead always gives equivalent braids. So perhaps this is something that could be further developed, so a different version of equivalence. But that's certainly something that is problematic, because you don't get one braid from the same K-lead, but it's different braids. So then there are a few questions you can ask about the braids. Basically, I've asked 2 questions. Is there any trivial K-lead? And are any 2 K-leads equivalent? With the braids that I found, none of the K-leads was trivial. So I've excluded the K-leads that were obviously trivial, where you just turn in a circle and then turn back again, or something like that. And no 2 K-leads were equivalent, unfortunately. So, but perhaps with a different numbering, as I said before, they could turn out to be equivalent. There were 2 approaches to answering these questions. So you can, I won't go into the details. They're just, art encoding is a very early algorithm for comparing braids, which is very expensive computationally, and then the handle reduction algorithm is more recent and a lot faster in practice. So now for the applications. Yes. So we need the third concept of configuration spaces, which is here the set of all points, the set of all configurations of n objects in a plane. And even though if you have danced to K, you're probably familiar with the problem that you do crash into each other. We do exclude that problem here. So no 2 objects are allowed to occupy the same place. And yeah, just for illustrative purposes, you can see that 1 and 2 would be distinct points in the configuration space. Now, for braids can be identified with paths through the configuration space. So, and in particular, they give collision-free paths. So you can move from one configuration of n objects to another configuration of n objects. And this is a great feature which should be exploited. And indeed, there's a problem where, this is a common problem, that you have a number of robots that you want to move around, and you don't want them to crash into each other. For example, you have them in a factory and they have to complete certain tasks without crashing into one another, and you also have obstacles in the plane. So there has been work on this done using braids. And in our case, so the solution to this problem is braids, because they give you collision-free paths, as I mentioned earlier, and they possess a group structure. So you simply define what the sigma i's are in a movement, and then you combine them and you keep collision-free paths. Yes, so, and well, lastly, the simulation program, this was the idea was to apply all the insights that were developed through the project to write a short program that would allow to simulate Cayley dances, and it would use the group structure of braids to make sure that you can just stick together different movements and combine your own Cayley. Unfortunately, I wasn't able to find an algorithm that would run fast enough for the program to work in an acceptable time. So yeah, this would be the end of my talk. Are there any questions?
Is a trivial Cayley?
Oh, the
Yes.
trivial Cayley, yes. So because none of the Cayleys was trivial, turned out to be trivial, we just, excuse me?
What's the definition?
Oh, well, the trivial Cayley would be a Cayley whose braid is trivial. So
Trivializable. I mean, it doesn't mean it's nothing has happened. It's something happened. I mean,
yeah. So you have complex
At the end,
movements.
they all unravels basically.
Yeah.
I see. Yeah.
And the further constraint is, of course, that it should be a Cayley-like dance. So you can't just sort of reverse one Cayley and stick it to the end of the other, which would always give the trivial
Exactly.
braid, but it should also be a nice dance.
Mhm.
So yeah, we've designed a trivial Cayley, which consists of two distinct movements that are then combined, and then their inverses are applied. Yeah.
You can't demonstrate with volunteers. No, it's too complicated.
Well, I need 8 volunteers.
Well, maybe that's too much. Any more?
So what did you say about the numbering affecting the equivalence of the braid groups or something? The numbering of the Cayley dancers.
Yes.
So how does it affect? I mean,
So if we go back to so you have the numbering of dancers here, right?
yeah.
And if you change the numbering, then you would so for example, say in this dance 1 and 2 swap place. Then if you change the numbering, then you have for example 4 is now the new 2. So instead now 1 and 4 are swapping place, because in the Cayley, this is a problem with the mapping which I didn't mention, is that in the Cayley you usually follow the dancers, but with the braid you have fixed positions. So you number the positions, and then the dancers, you have to imagine that the dancers come back to those positions. But yeah, if you number them in a different way, then the same movement will give a different, will affect different strands. Does that?
Yes, I'm not very familiar with the Cayley dancing, but do they have to follow the numbering that they have? I mean, the dancers, do they have to follow a particular number in the way they swap with each other?
No, they don't, but this numbering is just imposed from my side for the analysis. So in the Cayley, if you have the dancers here, and you number here 1, 2, 3, 4, 5, 6, say, and then these 2 dancers swap places, then you have a twist in the first and then the fourth strand.
Okay.
But if you say number this 1 and 2, and then these 2 swap places, and you have a twist in the first and second strand, which are they're not equivalent.
Yeah.
Okay, well. Thank you very much.
Thank you.
All the speakers.